So I'm happy to introduce Jamil Abo-Shaeer. So Jamil got his PhD working with Wolfgang Ketterle in 2004 at MIT. It was in the first decade of VEC, so of course he was having fun with VECs like a lot of us were. After that, he did a postdoc at Lawrence Berkeley Lab, then moved to Booz Allen, where he was doing support for DARPA for 4 years. Then he spent 4 years at DARPA as a program manager, moved from there to vice president at AOSense, which is a AMO physics-based company started by Brent Young and Mark Kasovich. And then in 2018, he co-founded and is now CEO of Vector Atomic. So I think he's going to tell you about what Vector Atomic does.
Okay. All right. Well, and if my voice gets a little funny, I'm just got the remnants of a cold, but I think I can make it through this. So thanks everyone for attending this. I'm Jamil Abo-Shaeer. I'm CEO and co-founder of Vector Atomic. And today I'm going to talk to you about deploying quantum clocks and sensors out in the real world. I think I would imagine that this is a little bit different from the typical JQI seminar in that it's application focused, but hopefully it's interesting to you guys to see how the technology that we develop out in the laboratory can make its way out into the real world and be impactful in the real world. So let's see. So Vector Atomic has flown under the radar for the last couple years, so you might not have heard of us. Our focus is on operationalizing atomic technology for navigation and timing. We were founded almost 6 years ago. We currently have 48 employees, and we're located in Pleasanton, California, in the Bay Area. A little bit different from many of the quantum startups you may have heard about. We're funded 100% through competitive government R&D contracts. We have no VC investment. We have no debt. We try to stand on our own 2 feet. And our focus is really on fielding quantum technology in pre-production units and trying to transition that to commercial products. We've already started to do that with some timing products, and I'll talk about that a little bit today. But the focus of our technology you're seeing in this strip of images, it is optical atomic clocks, optical synchronization modules, atomic gravimeters, and atomic gyroscopes. And I think exciting for us, the first 3 things, the clocks, the synchronization modules, and the gravimeters are all operating at state-of-the-art in their form factor. So in order to make this, get your sensor on this chart, we've had to you got to take these things out and show that they can operate in the world. And so we've fielded these sensors on land and at sea, and that gyroscope will be going to space soon. It's been delivered for deployment. Just to kind of key on our focus, and taking these things out in the real world, this slide summarizes a somewhat recent demo we did at RIMPAC 2022. This was a multi-nation at-sea demo of quantum technology, specifically for navigation and timing. We operated multiple systems aboard. You can see 3 optical clocks and an atomic gravimeter. Kind of a big demo for us to show that the technology can operate at state-of-the-art in the real world. So these clocks are highlighted in a recent paper on the archive that was recently accepted in Nature. And this strap-down atomic gravimeter, I'll talk about that a bit more, and that's used for gravity matching for navigation. So taking a step back, what's the excitement about quantum technology? I don't need to get you guys pumped. You got JQ quantum right in the title, but there's all this excitement that quantum technology is going to change the world, and I think a lot of that excitement focuses around quantum computing and what it will do in the future. And you can see some headlines when you search for quantum computing, all the wonderful and miraculous stuff it will do. And I think that is that's exciting for what the potential is, but the way we see it, quantum technology has already arrived. It's arrived in the form of atomic clocks, and so which enable GPS. So, GPS has really enabled our modern world, our transportation, our telecom, financial, defense sectors. All these things fundamentally rely on GPS to operate. And GPS has generated $1 trillion of economic impact in the US alone. And the thing about it is it's enabled by 1960s atomic clock technology. We would like to bring to bear more modern atomic devices, both clocks and sensors, to enable GPS 2.0, and hopefully unlock that next $1 trillion of economic impact. We're not going to sell $1 trillion in clocks, but they can have very big impact on the rest of the world. And examples could include higher accuracy GPS for autonomy, high bandwidth communication, mineral and oil exploration. And the exciting thing is that laboratory devices already have the necessary performance to enable these applications. They're the best measurement devices in existence. And so you can see that in this chart. And, the prime example is the strontium lattice clock or terbium clocks, at NIST and GILLIT that are good to a second in 50 billion years. They're the best measurement devices on the planet, bar none. And you can use a lot of the same tools and techniques to build best-in-class inertial sensors, magnetic field sensors, and electric field sensors. So great. We have that. And what's the catch? And I think you guys know that the catch is that these systems are not really ready for prime time. They're poorly integrated. They're not reliable. They typically require a small army of grad students and postdocs to operate them, and they're very fragile. So when we look at the problem, we think, okay, the performance is good enough. If we want to make commercial devices, we need to focus on all the other things to make these real. And that's integration, that they can operate in the environment they're intended to operate in. They're reliable, and cost is a big factor too. So if you came to me as a grad student and said, take your experiment and integrate it, into a portable and robust system, how would I have done it? I would have taken this default approach, which is kind of a lab in a box or ship in a bottle technique. You just take that very complicated thing, shrink down all the components, and build it into a smaller form factor. And that's, often, I think, maybe particularly in terms of quantum computing, the kind of initial approach to demonstrate efficacy. But that lab in a box style of integration is good, and you can prove stuff with it, but it's not really commercially viable. And here's some examples of what I would say are lab in a box style optical atomic clocks. These are great clocks. They're taking the highest performing devices and just kind of shrinking them down and making them mobile. They don't operate under motion, but they can be taken somewhere and made to operate. So the issue is that a lot of these devices really haven't been fielded out of laboratory environments. They're moved from one lab to another, and these portable devices are built from the same kind of research-grade components that we would use as graduate students and postdocs. So because of that, you end up with all the same complexity, all the reliability problems that you would of the laboratory ancestor. So these devices, are not built in mass quantities. They're kind of one-offs. And their build costs are very expensive, anywhere from $500,000 to $1 million a year. And so if you want to make real world devices, you can't just miniaturize the components and try to better engineer things. You really have to re-architecture the system. And if you want wide scale adoption, you have to build purpose-built devices, so not from Thor Labs, parts, things like that. You have to simplify the architectures significantly, and you have to make performance traits. At least that's our belief. So, this kind of captures the existing high performance clocks and inertial sensors by device classes, kind of roughly broken down into, into three classes. So the first is lab in a box. I mentioned kind of $500,000 to $1 million devices. And good examples of this are the Maser made by Microchip. Maser's play, as I'll show in a bit, a fundamental role in GPS. you know, they're serious and important devices. They're also the size of a small refrigerator, and they typically operate in a 1,000-liter environmental chamber. In terms of inertial sensors, this Micro G Lacoste FG5X is a falling corner cube gravimeter. It's the best absolute gravimeter on the planet, but still kind of a lab scale device that really has to operate in a laboratory setting. Pushing down to more integrated devices, this microchip 5071A, it's a cesium beam clock, and the Honeywell HG9900 is a ring laser gyro. These are kind of chassis scale rack mountable things, definitely cheaper, anywhere from $75,000 to $125,000. They sell hundreds of these a year. And if you can push down to fully integrated purpose-built devices like this chip scale atomic clock or a smaller ring laser gyro, I should say those ring laser gyros, that's 3 ring laser gyros, 3 accelerometers. It's a full 6 degree of freedom IMU. There's a lot of stuff in there. If you can push down to those levels, you'll make and sell even more. So I'm not trying to give you the business case here, but I think it's instructive to understand on, kind of how one approaches the problem. So this is basically a chart of how many of these things you sell a year based on their cost, and you can see a trend. So those, what's the punchline here? If you build expensive devices, $1 million scale devices, you'll sell, 10 a year. If you can build cheap devices, and cheap could mean $10,000 to $20,000, you'll sell tens of thousands a year. So that, there is a big need for them. And the cheaper these things get, the more of them you sell, not surprisingly. So when we set out to start this company, we wanted to really think about cost as a design consideration from the outset. So not start, can we build a strontium clock in a small portable box, but can we build a, simpler, maybe lower performing clock, shoot for something that's $100,000 scale, not $1 million scale. Now, presumably, many of you know what the kind of the tools of our trade are, specifically for atomic physics. This kind of quantum hardware is built from classical technologies. It's built from vacuum systems and glass cells, lasers and optics, and mixed signal electronics. So the metal and glass cells we just use to isolate the atoms from the outside world to protect this kind of delicate quantum state. Lasers and optics, we do all the preparation, probing, and readout of the quantum states for the measurement, and then the electronics and software just kind of orchestrate the whole measurement sequence.
Good question.
Yeah, sure.
So it's not the typical on your previous slide. So who are these customers who are going to buy these cheap devices? So I understand DoD is buying stuff.
Yeah.
Well,
So who buys 120,000 CSACs?
Yeah, I just can't imagine buy some clock from my garage.
I think that would be a bad thing to imagine because it's not something that you would imagine. You're absolutely right. Yeah. So great. Yeah. So how are they selling so many of these things? So I will turn on this laser pointer. These devices right here, this ring laser gyro-based inertial measurement unit, that goes into airplanes. That goes into airplanes that we fly across the country so that they can navigate in the absence of GPS. That will accumulate about 1.5 kilometers of error in an hour. So in a 5-hour flight, you'll be within 10 kilometers of the runway, which is good enough to kind of see the lights and guide the plane's captain in if they don't have access to GPS. So those they're selling hundreds of a year. They also go into defense aircraft as well, but commercial airliners. This 5071A goes into data centers, or a variant of it goes into data centers. So the big consumer is, Google, Facebook, telecom companies, things like that, that are required to maintain synchronization. They use GPS for their standard kind of synchronization, but they have requirements to be able to maintain some level of timing error if GPS goes away for some amount of days, tens of nanoseconds, hundreds of nanoseconds in a month. And so hundreds of those are sold. These other devices go into, well, this thing goes, they sell 50,000 of it. It goes into guided munitions. This, yeah, not the most pleasant. The CSAC is used underwater. They've sold 150,000 of these, and predominantly they sell them to the oil and gas industry, and they use them underwater to do some kind of, they use them in hydrophones, doing some kind of explosive, detonation, and then they look at kind of how the sound propagates, and they can tell what's under there. Is it rock? Is it oil? This type of thing. So,
But if I mean, so these gravimeters and interferometers, so if I understand Kasevich technology, so it's basically the bigger, the more accurate it is, right?
Correct. Yeah.
So if the small devices are guided munition, so that it means that error is pretty big, right?
Yeah.
So it's like a good idea.
Well, I'm not going to defend the use of them, but what you're saying is absolutely correct. So I told you that this is a $100,000 scale device, and so just to and I'll talk about this in a bit. For inertial navigation, you're doing, all you're doing is you're measuring your rotation along 3 axes and your acceleration along 3 axes, and you're integrating up the equations of motion. There's a lot of filtering things like that, but it's a simple idea of, if I can't rely on any external signals, I'll just measure my acceleration, my rotation, and I'll know where I am based on that. And then it's the error of those sensors, typically the bias error in the gyro, which sets how good your navigation area is. So that thing is 1.5 kilometers in an hour. This little device is, I think it might be more than 10 kilometers in an hour, but it, kind of given what we were talking about, it only flies for hundreds of seconds. And so the goal is to provide 10 meters for hundreds of seconds. So that's always true. There's always a trade-off between, unsurprisingly, between size and sensitivity. And then also bandwidth is the other thing that's being traded. So when these things are bigger, so a good example, this FG5X measuring gravity, it does a drop a second, or even a drop every 10 seconds. It drops a corner cube, and it's ranged interferometrically, and then that thing gets pulled back up, and you make another measurement. And so that's running at a low rep rate. The bandwidth of these sensors is probably hundreds of hertz, 250 hertz, something like that. So, these are the tools of the trade I mentioned. And if you want to make things that can go out into the world, you have to work on all of them. You can't just choose the ones you like, the vacuum system or the lasers and optics. Everything has to be worked on. And that's been the focus of our company. So you're seeing some of that technology here. So the top row is kind of, when I showed those boxes early on and said these boxes went out in the world, this is kind of the guts of those boxes. It's stuff that we have designed in-house at the system level, but it's built up from COTS components. So you can see, like, this laser system is a fiber laser system. We buy those components. We buy telecom-based components and splice them together to make our laser system. We design the vacuum system, but we don't, build the optics within it. In parallel, we're also working on these cheaper $10,000 scale devices, and you can see some of that here, building our own vapor cells in-house for our clocks, building kind of telecom style components that use integrated photonics, and then even developing our own ASICs in cases where you can't go to analog devices and say, buy a low noise current source. You have to kind of develop it on your own for this technology. So it's hard. This has been kind of a slog, and this kind of shows the progression of our company over these last couple of years, in starting with things using Thor Labs parts, and we still do that to do as you can see, like breadboard here to demonstrate kind of basic concepts and their validity. Someone on the okay, we're good. This guy is hybrid. and okay, so we're good. Demonstrate that. And once those are demonstrated, then we really work toward that integration. And I think, like I remember as a grad student, we would, do something kind of at the prototype level, but really good and impactful stuff. And then we would kind of leave it as a exercise for the reader in the conclusion of the paper to like, okay, and someone else will integrate this later. Now we try to be the reader, unfortunately, and that's hard work. So taking these systems and then really integrating them, and you can see kind of some of the subsystems that we build here, well integrated, stringing those things together on the benchtop to demonstrate performance. Once that was done, integrating them into a system with electronics, taking them out into the world, and now we're working on actually, manufacturing commercial products. So, that's just to kind of tell you about the philosophy. I'll show you, just performance now as we kind of talk about these systems. So I mentioned GPS, and GPS allows the world to run at kind of nanosecond levels. That's how we get our meter scale positioning. We would like to push that toward picosecond levels. And the way to do that is to go from microwave timekeeping to optical timekeeping. This just gives kind of a quick idea about GPS and how it works. GPS is fundamentally an RF timing network that's enabled by atomic clocks. So at the US Naval Observatory, which is 10, 20 miles away, they have a bank of 70 of these cesium clocks that I showed earlier, 20 of these masers that I also showed earlier, a couple rubidium fountain clocks. And that system resynchronizes these space-based clocks. There's 30 GPS satellites. They each have 3 rubidium clocks in them, and they're synchronized via two-way RF time transfer at the nanosecond level. So those clocks, over their orbit period, accrue about a nanosecond of error, and they get resynchronized at the nanosecond level. That gives us our kind of meter scale positioning that we all know and love. This is just a chart that shows how these things kind of perform over time. This is accumulated timing error, or TDEV, over how long the clock is run for these various clocks. I showed for GPS, you can see the maser in blue, why it's important. It basically provides the short-term stability for GPS. You can see those RAFs clocks accumulate about a nanosecond of error in half a day, and then long-term stability is provided by the cesium clock. So, how do microwave atomic clocks work? The simple idea is, these atomic clocks, we're referencing an oscillator that will drift in frequency over time, and we're, so we reference it to a narrow atomic transition that doesn't change. The properties of atoms don't drift or fluctuate over time. So, for a microwave clock, we typically use like a 10 megahertz quartz oscillator. That signal gets multiplied up to drive a microwave atomic transition, and then you just use feedback to keep that oscillator on resonance, and then you get your stable signal. The clock instability is governed by the Q of that transition. And so, kind of given this, if you look at that equation, if you boost up Q, or you boost up your number of atoms, your signal to noise, you can do better. And that's what we do for optical atomic clocks. So again, simple picture: instead of driving a microwave resonance, we drive an optical resonance. We no longer have quartz as the local oscillator. We'll have an optical signal, a laser, typically locked to a cavity. And use that same kind of feedback scheme to lock to an atomic transition. The problem is now we're running at hundreds of terahertz, and that's not a usable frequency. So then we add in one of these frequency cones to basically coherently divide down that signal to maybe 200 megahertz, and then down to a 10 megahertz output, again, that the world can use. That addition of a frequency cone, that's a little piece in the chart right here, but I think a lot of that's, something that was a Nobel Prize winning experiment, in 2005. So not a simple device. So if we, the goal is to push toward laboratory timekeeping, and you know, we already saw this Gila strontium lattice clock. That comb also, frequency comb plays an essential role in this NIST kind of pulsed two-way optical time transfer method, and they've been able to show femtosecond level synchronization over hundreds of kilometers in free space. So these are kind of the two technologies that we want to, you know, potentially work from. You know, why are these exciting? Well, look at the chart again and look how these things perform versus what's out in the world. So those red dots are the Gila strontium optical lattice clock. That thing, in theory, if it could run, you know, could hold a nanosecond of timing for 15 years. And this NIST two-way optical time transfer scheme is much better at femtosecond levels, you know, can kind of keep up with that timekeeping. So, you know, what's the idea? Well, we add lasers to the system, and lasers have really revolutionized timekeeping. They're also, you know, and, you know, all atomic physics, they're also what make all these systems terrible and unreliable and hard to deal with. So we want to use them, but use them sparingly is the rough idea. But you can see this commercial clock, the 5071A, it's kind of the gold standard for timekeeping. Cesium beam, you know, quartz, OCXO, it can hold a nanosecond for 3 hours. They sell hundreds of them a year, and they operate for 7 years. They fit in their 30-liter 3U rack mount device, no lasers in them. That's the key. If we look at one of these R&D clocks, say a strontium or ytterbium optical lattice clock, you trap the strontium and ytterbium, you have a cavity stabilized laser as your local oscillator. As I mentioned, nanosecond of timing error in 15 years, if it could run that long. These things are built in the, you know, takes 2 years to build one, anywhere from $1 million to $2 million, and I would give them about a 7-hour warranty. You know, between, you know, graduate students relocking the system. They're large systems. They require kilowatts of power and PhD level operators. And really, if you think about it, it's because they have 8 to 12 lasers. Typically, you know, say for strontium operating anywhere from 460, you know, 689, 698, maybe 812, all these different kind of oddball wavelengths where you build ECDLs to hit all the wavelengths you need. And so this is really kind of going at the problem brute force. You pick the atom that gives you that's the best possible timekeeper, and you build the laser system around it. Our philosophy has been to pick the best lasers and then see what atoms that we can drive with them. So the idea is to build the simplest optical clock, not necessarily the best. And our competition isn't, you know, Jun Yi and Andrew Ludlow in Colorado. Our competition is the Maser, those clocks that are already out there in the real world. And so you can see, you know, what's the simplest thing that we can do? It's basically saturated absorption spectroscopy to the nth degree. And we choose iodine. We choose iodine because it has transitions at 532, so we can double from 1064. Our comb is a 1550 erbium fiber-based system. So, you know, if I were to bet my life on 2 lasers, and I have in some sense by starting this company, those are the 2 lasers I would choose. And that's because other industries have spent billions of dollars making them robust. So that's a great starting point. And then we, you know, if I went back and looked at my graduate school experiment, it's still there 20 years later. But it's like a Frankenstein experiment. They've built more and more onto it. They've added more lasers to the system. And, you know, the idea is to push performance. And that's what we do in an academic environment. We try to do things that haven't been done. What we do is try to take as much away as we can without, you know, without compromising the system so much that we end up worse than, you know, the box size system. So this clock doesn't use a cavity. It doesn't use any laser cooling. There's no consumables. It's just a multi-pass vapor spectrometer. All the optics are bonded down, so we don't have a bunch of, you know, mounts that we tune. We kind of actively align everything and nail it down as best we can, fully purpose built. It will operate at high bandwidth because it's a vapor cell clock. 2 lasers are the least we could use for an optical clock. Again, the cone laser and the clock laser. And then that also makes the electronics substantially easier because you have a lot less lasers to lock. So what's our goal? Is there a question?
Yeah, this is Bill.
Hey, Bill, what's up?
So this looks a lot like the iodine stabilized helium neon laser that I first saw when I came to what was then NBS in 1978. So
Yeah.
But there must be some additional magic here.
So there is. Okay, so yeah, so what we're not doing is we're not doing 2024 atomic physics and 2024 packaging. I would say this is more like 2005 atomic physics. Like before Junyi was working on strontium, he was working on an iodine optical clock. So the one addition is that there is the comb in it, and that allows you to actually divide down from hundreds of terahertz. And then, this is shown here, but if you're really trying to use this as a standard, yeah, we draw, in the simple block diagram, there's housing and a thermal shield, and, we stabilize temperatures and everything, but you have to do this to a very high degree. If you're doing spectroscopy like this, if you build a strontium clock and you turn it on and it works, you get a great signal out of it. For this, we have to really operate at, very near the limits. That means we have to temperature stabilize things. We have to control reflections. We have to control RAM of the laser. And so a lot of these things like temperature controllers, Bill, and all this kind of stuff, this cell is stabilized to a millikelvin over, over more than a week. And so the kind of iodine system that you were looking at probably wasn't. It was a longer cell. Also, this is kind of a multi-pass small cell. So there's a lot of engineering, I would say, that goes into it. And still, I think an important point to make is this work kind of takes as much creativity as you would, use as a grad student or a postdoc. It's just, we're not applying it toward, again, performance. Maybe I already made that point. So Bill, does that answer some of that question? I think what you're saying is true. And it is, can we hit these very aggressive numbers of like a maser? Can we split the line to the nth degree? Because that iodine transition isn't narrow. This isn't like, 10 hertz transition or something. It just means that everything has to be done in a very tidy way. You have to care about the laser noise. You have to care about the temperature stability, RAM, these types of things.
Are these 1064 lasers a whole lot better than say a Heaney that nobody uses anymore?
Yeah. And so I think you can, I'll show you the performance. I think I already, let me skip that. So I'll get to the performance and you'll see how we're doing. In fact, I'll get to it on the next slide, but I'll just say we built 2 of these boxes, that are nearly self-contained. They ran off an external laptop and an external power supply. And we took them to NIST, and that's kind of NIST in Boulder. That's the best place to characterize your clocks. And here is the performance we saw in these systems. So you can see we are pretty similar. We're kind of near our target of offering maser stability in a much smaller package that can also go out in the world. Those masers are very temperature sensitive. They are very magnetic field sensitive, vibration sensitive. So again, we're not going for these absurd levels that you'd see in the laboratory for optical clocks. But what we see is if we add lasers into the system, we can get basically the same performance in a box that's a 1/10 of the size. And I think the other important point is that kind of operate way they go out into the world and operate. I don't know that a maser is on the ship. We've taken these and operate mentioned earlier for about 3 weeks. They see big templings. They see, vibration, and motional effects, just large changes in magnetic, which often, can cause problems. You can see real problems, basically in a glorified shipping container, and some power on our clocks were right here of AC and indirect line. And so the question is, how do they operate now? Operate in this benign instrument, and that's the open circle data here. And what you see is it's pretty similar. That's exciting for us, is that we can get these high levels of performance in a more challenging environment. Kind of shows some of the power of these systems. We built these things. We wrote a paper. People were excited. They said, "Great, can we buy one of these?" And we said, "Absolutely not." And that's because if you were to open up that box, you would see, there was kind of a hodgepodge of off-the-shelf electronics to just get it out in the world. I mentioned this external power supply running all those COTS electronics. But we've continued to work, and this is the thing that we are starting to sell. We call this Evergreen 30. And now not only are we hitting these levels of performance, or kind of hitting the maser performance, we're actually doing better than it. So we're excited about that. So 10 times smaller than an active maser, better phase noise, better short-term stability. I think what's important about this is it puts out 10 megahertz and 100 megahertz, but for things like optical metrology, it also has a 1064 signal. So, for things like quantum computing, if you want to lock a bunch of lasers, you might buy a comb and a cavity. And in this case, this can take that place, and the drift of this system is about 10,000 times lower than a ULE cavity. It also has a 1560 comb output. So if you want to do extension, to other wavelengths, you can do that. So we're excited. Took a long time to get to this point, but now we're starting to take in orders and start building these things, and we hope to have kind of more wide scale of a product launch later.
How much does it cost? What do you mean? We're going to ask that.
In these quantities, it costs the same as the maser. But it's a factor of 10 smaller in size and gives other outputs, things like that. But our goal is to get it down to more like that 5071A cost. But we're building these things, not surprisingly, these are built by our senior physicists right now in 1s and 2s. The next thing is to really go toward volume manufacturing, and we're setting that up right now so that we could build 25 to 50 of these a year. But maybe it was a good question, kind of, because that's actually all captured in this slide. So you can see the size of this thing, to scale versus the maser. And again, that maser typically operates in an environmental chamber. And it's not just that we are 10 times smaller, but we're lighter, we consume less power, better phase noise, better short-term stability. So we can beat the maser on all axes except for cost right now. So that was actually a great question, Bill. And we're pretty similar, in production costs, but again, that's in building it in 1s and 2s, and we need to bring up that manufacturing. And, in doing that, we have really focused on in-house integration and kind of building up our own supply chain for those critical components. So if you look at what's in that box, the guts of it, you can see a picture of that iodine spectrometer, where we, work hard to stabilize the temperature, make sure the bench is rigid, all this kind of stuff, so it can operate in dynamic environments. Small clock laser, very small frequency comb, and custom electronics are going into it. And so, yeah, all that stuff is kind of, we bite the bullet and we try to build it in-house. And it's an advantage because we can really reduce the system size and cost by doing all the integration ourselves and making sure it's done in a sensible way. The example is, if you were to just buy a frequency comb from Menlo, it would be $200,000 to $300,000. It would be the size of this box, and it would consume 30 watts. By doing this stuff in-house, we're able to build the full frequency comb into 2 liters, and it consumes 8 watts. Go ahead.
How long does it take?
A box like this takes some time. Yeah, I mean, this is something that, again, like you guys were doing R&D to get to this point, and then now we're taking the same people and saying, hey, stop doing that and build a couple of these boxes. So our goal, we think we can build one of these a week. That doesn't mean, but that's batch manufacturing. It doesn't mean one is built each week. It's like nothing happens and then 25 show up after 6 months, build these things in series. Go ahead.
Yeah, so you're talking about the size and the power consumption as opposed to like a Menlo comb.
Mhm.
What about the performance?
Good question. So this can support, I would say like they're super high performance ones. They're probably a little bit better in performance, but this can support a strontium clock. So it can support the cutting edge clocks. Okay, so there's this other piece. Let's see, this is so there's this other piece of things, which is, it's one thing to build the clocks. You also need to be able to, and get high performance. You also need to be able to synchronize them. That's what you need for a timing network. And so we have also been working to integrate this kind of NIST scheme of comb-based time transfer. And you can see kind of the NIST setup here, and we've been able to kind of put it into similar size terminals to our boxes, 35-liter devices. If you want to know more about this NIST scheme, and it's an awesome scheme, you can look up the paper. But our focus is really on integration and robustness. Robust frequency combs, optics, electronic integration to get these things down. And we also leverage integrated photonics to make the system smaller, and you can see that here. Kind of critical parts of the system. There's a heterodyne module that does the measurement, and you can see how it's built. Kind of stringing together fiber optics by NIST, and we're able to basically imprint those fiber optic, all those lines onto chips. So you can see them here. There's 3 modules. This is roughly to scale. Not only does it make the system smaller, but it actually makes the system, more robust. There's, by using photonic integration, we can minimize kind of any out-of-loop paths. We can thermally stabilize the whole system in a fairly straightforward way. So we built those modules and we took them to NIST and kind of hot swapped them with their system. You can see this here. They do this time transfer out of these telescopes out to Table Mountain, 15 kilometers away, and get the return. So we were able to put in these systems, in a couple hours and get this up and running. And here's the performance here. You can see in these green triangles, that's over this 30-kilometer free space link. So we're able to stay below 10 femtoseconds over those distances. And, beyond just kind of doing that, we're continuing to work on integration. So now we've made these transceivers that are sub 10-liter scale. And those have 2 frequency combs in them. A lot of other stuff. So, kind of quickly, we're still working. We don't just stop at the 30-liter device. I said we're doing R&D. So what's our goal? Our goal is to go from the 30-liter device to the 5-liter device, ultimately to a liter scale device that could operate in a satellite. There are going to be performance compromises in the system, but we can still do well. And so this kind of shows, just quickly building these systems smaller. And so here we have now a spectrometer that's 1/10 of a liter and a laser system, the full laser system, 1/10 of a liter. You can see a quarter right there. And this performance is still fairly close to maser level performance, or close to that cesium level performance in a much smaller package. So I don't have the frequency comb here. We weren't running that, but we also have, that's at about 0.2 liters right now. Much simpler device. It actually uses a COTS 532 laser that costs a couple $100. So, big change in making these things cheaper. Let's see how we're doing on time. Okay. I tried to focus, I think we're further along in the development of these clocks, but I want to talk about kind of the equally important piece of what we're doing, which is building atomic inertial sensors as well. So we want to enable operation in GPS-denied environments, and we do that by first, one of our pieces is a deployable atomic gravimeter that we can operate at sea. Every once in a while, you'll read in the headlines that some submarine ran into an undersea mountain, and you'll think, why did that happen? Like, were they not paying attention? And the reason is simple, is they want to maintain covertness. And so they don't want to broadcast anything because others might be listening for them. They don't want to put up a GPS antenna because satellite can see that from space. And so they rely on inertial navigation I mentioned earlier, which is just measuring rotation and acceleration along 3 axes, and again, integrating up the equations of motion. The better you do that, the longer you can go, and you can just think of it as this little air bubble is growing around you. And these high-value platforms use very expensive inertial navigation systems. They cost, several $1 million, but they still accrue about 1 kilometer of error, in 3 days. And so over 30 days, that's 10 kilometers of error. And you could see how, if you're only relying on that, you might run into something you didn't mean to. So, what are we doing? Through this project with ONR, we've developed this gain sensor, and we're trying to do navigation aiding by measuring local gravity and feeding that back in to kind of our navigation solution. So the goal is to be able to operate for longer in GPS-denied environments, and to do that in a form factor that could go into some unmanned, submarine. So the technique is straightforward. We're going to measure local gravity. We're going to compare it to measurements from satellite altimetry of gravity maps, and use that information to navigate. Challenge here is that these sensors have to be rigidly mounted. They operate in what's known as strap down. They're bolted down to the system. There's no motion stabilization. There's no gimbal. They're hard mounted down. And so what do we need to do? Well, these fluctuations are at the micro G level, or milligal level, over 100-meter scales. So you need to be able to basically measure gravity at the micro G level while you traverse 100 meters, and you do that in about 10 seconds. So operating an atomic gravimeter at micro G levels is pedestrian. The best gravimeters that operate in laboratories operate at nano G level. Operating them in the presence of ship motion is very hard, and operating them at high bandwidth, so that you're making measurements on a time scale faster than the ship motion, is also very hard. So on a ship, local gravity might be changing, or there might be acceleration from the ship in heave motion that's as much as 1/4 of gravity, and now you're trying to pick out this micro G measurement out of these large motions. And I think to kind of illustrate that, you can see this is a ship we've operated on. So you're trying to measure micro G levels, and you're operating on this ship that's rocking back and forth and going up and down. So you have this huge background on, acceleration on top of your motion, and you need to pull this kind of needle out of a haystack. And how do you do that? That's a challenge. And so this is the system we built for it. Some of the let's see if some of the guts for the system. You can see this is our 8-liter sensor head. It's a hybrid sensor head. So it not only uses an atomic gravimeter, it uses a conventional sensor as well to kind of boost up the bandwidth in the system. A very robust fiber laser system operating at 1560. I should say this is rubidium, so it's operating at 780. We have a 1560 system that we double to 780. And then you can see, like, you know, we have to do all the motion testing and things like that in the laboratory to make sure it can operate, you know, in a real world environment. So this is data in the laboratory. You know, I mentioned these kind of, a micro G is the same as a milligal. So we're trying to, on kind of a 10-second scale, integrate down to those milligal levels, and we're able to do that and hold it, you know, indefinitely over, say, 30 days. So, you know, just an example for these systems, we've done multiple 30-day runs. The things operate, you know, autonomously, fault-free, and they'll make, you know, 100 million measurements without any faults. So that's probably about a factor of 100 more measurements that I made in my graduate school career, you know, if not more than that. So, you know, we took these things, we put them on ships. We've done multiple tests at sea. You know, I know COVID was a bad time for everyone. It was a bad time for us also. And at the beginning, you know, one bright spot is we got this thing on the network, and we had one of our scientists go home, and he worked on a bunch of routines and remoted into the system and worked on all these startup routines so that we could quickly bring up the system. So it can go from unboxed to operating at spec in 15 minutes. We've operated, you know, on ships with 99% you know, uptime. In this case, the only downtime was when we had a Windows update error in the system. So we all deal with the same problems. We'll go to an embedded controller in the future. And we were able to operate, you know, under pretty rough conditions. You saw the conditions that we were operating at, and operate at spec. So this is just, you know, some quick data from this system. And so what you're seeing here is the gravity anomaly measured over time. And so that's the change in gravity. That's versus the satellite maps. And really kind of what's important is the residual. It's what we measure versus the satellite maps. You can see that here in red. And so we're able to track over several days local gravity, you know, and local gravity anomaly, and compare, you know, at the milligal level with these satellite maps. I think what's important is also that there are multiple satellite maps, and they disagree at the milligal level. So we think we have reason to believe that we're actually doing better than that and hitting the spec. Ultimately, those gravity anomaly measurements get turned into navigation aiding measurements, and that's something we've worked with Johns Hopkins on, and they're able to show reduced error in our navigation using this atomic gravity measurement. So that is exciting. Last thing, you know, building atomic devices for harsh environments. We have also built an atomic gyroscope for space deployment. This is a very challenging problem. Space is the hardest environment to operate in. Maybe it's benign when you get there, although there's radiation, but surviving launch is a real challenge. So this is a Pathfinder rubidium atomic gyroscope that we built. It's called QUIX, and you can see some of the hardware we built. You got to, you know, build specialized electronics, you know, lasers, things like that. Do a lot of testing. You know, this is just to kind of show, you know, how these things may operate. So you can see, like, we had to shake this thing at you know, 6G RMS, the whole system. We temperature cycled the components from, you know, -30 to 50C multiple times. We gave the components a radiation dose that was equivalent to 10 years of operating in space, and all that stuff survived, and we were able to build the system. You know, I think a lot of what we learned here will ultimately get translated down to what we build in just commercial devices that operate in the real world. But it's important to go through kind of these challenging environments and figure out how to operate in them. And this is something we also, you know, we had a partner, Honeywell Aerospace, and they helped us with the space qualification, sensor testing, things like that. This is just the built up system, you know, before we put all the covers on it to get it ready. And it's now bolted on the side of a of a platform, you know, a rocket that will be going to space. This is just the, let's see if this is just the last piece of it. So, you know, kind of here's the system. And you'll see how we do our special effects here at Vector Atomic. So there's no magic in anything. It's just a bunch of hard work. You know, this guy down here, he designed, you know, all that. He gets the honors of the glory shot. So with that, you know, that's it. Certainly we're thankful to, you know, we have a very hardworking and bright team. And then we have a lot of sponsors and collaborators. So with that, thanks for your time. Happy to take any questions.
Well, in your system where you're still building 1 and 2
Mhm.
for how long, are you making modifications on each of those 1 and 2?
Yeah.
Yeah.
Yeah. And so, you know, the first thing that went on the ship, we called that our Gen 1 device. It was not surprisingly the first ones we made. Those ones that are going now are the Gen 2 device. We're working on a next version to integrate the electronics more. So we're starting to sell those Gen 2 devices in small numbers, but the one we want to manufacture in larger quantities would be that Gen 3. We have to hire different staff to do that. We have to hire technicians. We started to hire you know, lower level staff to do that. I mean, I think the thing is, you know, the people who are good at designing those first things are not the people who want to build 100 of them, not surprisingly. And we need to get those people designing the next cool thing. At the same time, we get engineers who do want to build, who are excited about building 100, you know, of these things. And so it's a different mindset, and we just need to staff appropriately. But we can't hire those people until we have the recipe. And so, and as atomic physicists, we always want to make things a little bit better. Like everyone, all the atomic physicists want to get that performance better, and they'll do it forever. And you have to at some point say, stop, this is good enough. And so we're trying to do that now.
Yeah, so I have a question about your interferometers, second floor gravimeters that you discussed.
Okay.
So I see there is a lot of kind of DoD flavor to this work. So if I imagine the part is sort of trying to actively jam your sort of operation of your satellite for GPS. So is it sensitive only to inertial forces, or you can imagine some environment where, let's say, electromagnetic field can
Yeah.
the
So
accuracy?
there's two parts of that question. You know, a good thing about gravity is that you can't jam gravity, right? You know, so that's a good signal that is around, but these sensors are sensitive to more than one thing, you know, and so we make some interferometric measurement, and folded into that was the magnetic field changing, you know, was other stuff happening which spoils that measurement. So we calibrate the thing, you know, in one case, and you know, we could show you how magnetic field was varying over say one of these long voyages, and it varies by a fairly significant amount. So the answer is, yeah, it's an alkali atom. It's sensitive to magnetic fields. It's sensitive to thermal, you know, issues as well, because you're referencing these atoms to some laser, you know, that so the atomic properties don't drift, but other other things do. So all that being said, you know, magnetic field is a big thing. We put shields around it. So you put mu metal around it, and you can knock it down to the level that we're able to measure, you know, at those levels. You know, I don't know if someone was actively trying to do something, you know, maybe, but
But you could imagine this scenario if you deploy it in a combat environment, probably they're not going to be very friendly for it.
well, you're underwater, and so how far do those signals propagate, right? You know, that's also, I mean, that's why we can't get GPS. And so I think it's unlikely if someone is nearby you like that and doing something, that there's probably bigger problems than that. But a good point is that these interferometers integrate all stuff into them that they measure. And you have to disentangle that, or you have to do things to limit that. And so we do that. We stabilize the temperature of the bench, and we put mu metal shielding around the box, sometimes multiple layers.
Obviously very example of why that be better. Do you have something similar for the better clocks and
Sure.
optical synchronization?
Sure. So, so in the future, we're all at some point going to be in autonomous vehicles, right? Presumably. And right now, when you're driving down the road, your GPS is good enough that that you're which probably side of the road you're on, or maybe not, and it just sees that you're moving in a direction and guesses based on that. But it can't keep you in your lane, right? And so a nanosecond, or 3 nanoseconds is a meter. And so if that's the level that you're operating at, you're not going to do better than that. In cases like that, or if you're landing a plane where there's human lives involved, they want to have like centimeter scale accuracy. And so you need to push up to, I probably could have here. Yeah, I could have maybe explained this better, but if you want, I put 3 millimeter position because you usually want to be like factor of 10 tolerance better than 3 centimeter. You need to know your time to 10 picoseconds. And GPS can't do that today. And so if you want to, have that as a modality in low Earth orbit satellites, there are other issues because you can say, well, these signals propagate through space, through the ionosphere, and that kind of scrambles the signal. So one of the ideas is to just get lower in the ionosphere. And so if you're operating in low Earth orbit and these kind of proliferation like Starlink or things like that are operating at those levels, they see less of that. And so they can push to these kind of centimeter scales. The other thing you could do is put them as beacons along the road. That can give you better positioning. It can also give you more reliability on your GPS signal in general. So if you're landing a plane, you want to know like, I'm a meter above the runway and not like randomly 2 meters, or have these kind of jumps as well. And so that kind of tightens up your whole thing. There are a lot of ideas for. The problem is that everything is built around the clocks that exist today, and you give people better capability. Now they have to build to it. So radio astronomy is one thing where they use masers, and that's something where there can be some benefit because the phase noise of these optically generated down converted systems are always, oftentimes significantly better. There's, I've talked to people at Facebook and things like that. They have a lot of interest in synchronizing like GPUs, that are running at multiple gigahertz, to make sure that, they're all sequenced correctly. I can't claim that I totally understand that, but the things are clocked at like 2.5 gigahertz. So they need to know their timing to 50 picoseconds, something like that. And that can allow them to more efficiently, run this computation. I'm not trying to link us to AI. I know that's a good thing to do. And if I can, all of a sudden we're worth 10 times the money, but, there are ideas for higher bandwidth communication, things like that.
All right, how about this will be our last question.
Thank you. Very nice talk. In your clock slide, you showed that you're using iodine as a reference species for the clock. Wondering, besides having lines at 532 nanometers, are there anything else about iodine?
Yes. Yeah, that's a good question. And so, a competitor clock to this is there's a rubidium-2 photon clock. And that is very similar, and it uses, it could use a doubled 1550 system, and 1550 is better than 1064. You can get better lasers. But a couple things that make iodine better are the AC Stark shift is lower than, say, for rubidium. There's a subtle point, and I don't have a slide here on that, but what do we care about in these systems? It's the temperature, it's Temco, how these things change with background temperature. And iodine in these systems or any of these things, if you raise the temperature, you have like a little piece of iodine there, and the vape, as you raise it, more vapor goes into the system, and that will spoil your measurement. And that's why we take such pains to stabilize the temperature of that cell. With iodine, because it's all because it has a low melting point, you can fill the cell with just the exact right amount of iodine. So it's all in vapor at room temperature. That's called depleted cell filling. And that's something that we do. And it takes away that dominant temperature error in the system of the iodine going between metal and vapor. And it just puts everything in vapor. As long as we operate it above that, kind of that characteristic fill temperature. And so that reduces the Temco in the system versus if we were doing the standard technique by like a factor of 20. And that's why we are able to, get performance at these kind of maser levels. And so if you were to look at typical rubidium-2 photon results, they would suffer more from those temperature issues.
Okay, let me remind the students, postdocs, 3 p.m. Atlantic 2117, and let's thank Jamil again.